Hello, my dear dreamers and cosmic travelers, and welcome back to another sleepy science story, where we soften the edges of the day and explore the wonders of the universe, all from the comfort of your own mind. As you're settling in, finding that perfect, cozy position, I want you to close your eyes for just a moment and picture this: a place in the cosmos where the laws of physics as we know them simply break down. A place of ultimate mystery, of profound darkness, and of breathtaking possibilities. What would it be like to journey there? To truly fall into the heart of a black hole? That is our voyage tonight. We are going on an immersive, thought-provoking journey to answer one of the most compelling questions in all of astronomy. What really happens when you fall into a black hole? We'll explore every theory, from spaghettification to wormholes, and unravel the secrets hidden beyond the event horizon. So, get comfortable, let your imagination float free, and allow your thoughts to drift among the stars. Before we dive into the abyss, if the sound of my voice is a familiar comfort to you, if these journeys help you unwind, learn, or simply drift away, then consider subscribing to Hafi Sleep. It's the easiest way to make sure our next adventure finds its way to you. And if you're enjoying this journey, giving the video a like is a wonderful way to let me know. I always love hearing from our community. It feels like we're all exploring the cosmos together, no matter how far apart we are. So, if you feel like it, drop a comment down below and tell me where in the world you're listening from and what time it is for you. Are you watching with the morning sun, or like many, is this your nightly ritual to unwind before sleep? It's always fascinating to see our global family of stargazers gathered here. Okay. With that said, it's time to dim the lights, quiet the noise of the day, and begin our descent. Let's explore what happens when we fall into a black hole. Have you ever looked up at the night sky, seen that vast expanse of twinkling lights, and felt a sense of wonder? What's out there? Are we alone? What are the true limits of reality? Of all the mysterious wonders the universe has crafted, none captivates our imagination and our fear quite like the black hole. A place where the laws of physics as we know them break down, where time and space swap roles, and where the very fabric of reality is stretched to its absolute limit. What would it actually be like to fall into one? Is it a cosmic shredder, a gateway to another universe, or the universe's ultimate vault, locking away secrets forever? Today, we're going on a journey together. A thought experiment. An exploration of the unknown. We're going to fall into a black hole. We'll experience every terrifying, baffling, and awe-inspiring moment, from that first irresistible tug of gravity to the final, unknowable destination. I'll be your guide, your fellow traveler, and your narrator, explaining each phenomenon in simple, plain language. We'll lean on the brilliant work of scientists like Einstein and Hawking and explore the very frontiers of what we think we understand. So take a deep breath. Settle in. Let your imagination float free. It's time to venture into the cosmic abyss. First, let's understand our destination. What exactly is a black hole? Forget the complicated math for a moment. Imagine space as a vast, stretchy rubber sheet, the kind a gymnast tumble on. Now, place a heavy bowling ball in the center. It creates a deep dip, right? Any nearby marbles would roll toward the bowling ball. That's gravity, in a simplified form. A star, like our sun, creates a similar dip in the fabric of space-time. But a black hole is like a weight so infinitely heavy, so incredibly dense, that it doesn't just make a dip. It pulls the rubber sheet down into an infinitely deep, narrow hole, a puncture in the fabric of reality itself. It's a region of space where an enormous amount of mass is packed into a tiny volume, creating a gravitational pull so strong that not even light, the fastest thing in the universe, can escape it. They are cosmic traps for light and matter. This is why they are black. They emit no light of their own and trap all light that falls in. They are, in essence, invisible one-way doors in our universe. How does something so extreme come to be? For the most common kind, the stellar mass black hole, it's a dramatic story of stellar death. Think of a giant star, much more massive than our sun. For millions of years, it burns bright, the intense heat and energy from nuclear fusion in its core pushing outward, balancing the massive weight of its own gravity pulling inward. It's a cosmic tug of war, and for the star's life, it's a stalemate. But eventually, the star runs out of fuel. The fusion stops. Without that outward push from the core, gravity wins, catastrophically. The star's core collapses inward at a staggering speed. If the core that remains is more than about 3 times the mass of our sun, the force of gravity is unstoppable. It crushes all that matter, an amount that could be several suns' worth, into a point so small it's effectively dimensionless. This is the birth of a black hole. But not all black holes are created equal. Our volunteer for this journey is a stellar mass black hole, about 10 times the mass of our sun. There are also the monsters of the cosmos, supermassive black holes. These are millions or even billions of times the mass of our sun, and they live at the centers of most galaxies, including our own Milky Way. Their origin is still a bit of a mystery. Did they start as smaller black holes that merged and ate their way to gargantuan size, or were they born supermassive in the early universe? We're still figuring that out. For our trip, we'll stick with the smaller stellar mass variety. The experiences are different, and we'll touch on why as we go. So, we have our target. Let's begin our approach. You are the captain of a state-of-the-art exploration vessel, the CSS Curiosity. Your mission: to conduct a close-range survey of a newly discovered black hole, designated V74, about 10 solar masses, floating in the emptiness about 1,000 light-years from Earth. Your ship is a marvel of engineering, equipped with every sensor, shield, and safety system imaginable. But as you'll learn, some forces in the universe don't care about your technology. For a long time, as you cruise towards it, V74 is just a patch of empty, black space, blacker than the black around it. This is because the black hole itself is invisible, but soon you start to see its influence. First, the light from stars behind it begins to warp. They don't look like points anymore. They look stretched and smeared, forming a shimmering, undulating ring of distorted light around the central darkness. This is because the black hole's immense gravity is acting like a giant lens, bending the paths of the light rays from those distant stars. It's a beautiful, ethereal halo of twisted starlight surrounding the abyss. You also notice a disk of brilliant, hot gas and dust swirling around the black hole's equator, like water circling a drain. This is the accretion disk. Material, gas, dust, maybe the remnants of a torn-apart star, is caught in the black hole's gravity, orbiting at ferocious speeds. As these particles rub against each other in their frantic dance, they heat up through friction to millions of degrees, glowing with intense X-rays and gamma rays. It's a blinding, violent whirlpool of energy, and your ship's sensors are screaming with warnings about the lethal radiation. This is not a friendly neighborhood. Now you decide to fire the ship's engines to hold a steady position, to just observe for a while. You're at a safe distance, you think. But you notice something strange. To maintain your position, to not get pulled closer, your engines are working harder than they should. You're constantly burning fuel just to stay still. This is the first true taste of the black hole's power. You've crossed a boundary known as the innermost stable circular orbit, or ISCO. In simple terms, this is the point where normal, stable orbits become impossible. It's like trying to balance right at the very top of a perfectly smooth, steep hill. The slightest nudge, and you start rolling down. For you, that nudge is the constant, relentless pull of gravity. From this point on, it will be a constant, energy-draining fight to not fall in. Let's pause here for a moment at the edge of the precipice. Imagine you have a companion, a brave scientist on a space station far, far away, watching you through a powerful telescope. We'll call her Commander Layla. Her perspective and yours are about to become very, very different. This is one of the strangest parts of our journey, the concept of relativity. It's not just everything is relative. It's the idea that space and time are woven together into a single fabric called space-time, and gravity can stretch and warp that fabric. As you sit there, fighting with your engines, Commander Layla on her distant station sees something bizarre. The light coming from your ship starts to change. The intense gravitational field of the black hole is acting like a drain on space-time itself. The photons of light that carry your image to her have to climb out of this deep gravitational well. As they do, they lose energy. Since the energy of light is tied to its color, losing energy means the light shifts to a longer wavelength, towards the red end of the spectrum. This is called gravitational redshift. To Layla, your ship, which was once brilliant white, is now looking pink, then deep red, and it's getting dimmer. It's as if your ship's batteries are dying, but it's really the light itself being sapped of its vitality by the black hole's gravity. Meanwhile, on your ship, everything seems normal. The lights on your console are bright. Your clock is ticking away seconds as it always has. You are experiencing time passing normally. But from Layla's perspective, something even weirder is happening. She sees your ship, and everything you're doing, starting to slow down. It's not a technical glitch. It's time dilation, a key part of Einstein's theory of relativity. The stronger the gravity, the slower time passes. From her vantage point, far from the gravity well, your time is literally stretching out. Your movements look like you're trapped in slow motion. If you were waving, it would be a languid, dreamlike wave. If you were speaking, her receiver would be picking up your words drawn out and deep, like a record player slowing down. This is real. It's been tested with incredibly precise clocks on airplanes and satellites. Time for a GPS satellite in weaker gravity actually runs a tiny, tiny bit faster than for us on Earth, and if we didn't correct for it, your phone's map would be useless in minutes. Here, near the black hole, the effect is monstrous. As you get closer from Layla's view, you will get slower and slower until you appear to freeze completely, a statue poised at the edge of eternity. For her, you will never actually cross the final threshold. You will fade to red and then to black, frozen in time. But for you, the journey continues. It feels normal. Time passes as it always has. This disconnect between your experience and Layla's is one of the most profound and mind-bending aspects of relativity. There is no single, universal now. Your reality and her reality are literally different. Encouraged by your initial surveys or perhaps growing overconfident, you decide to get a little closer. You reduce the engine power slightly, and the CSS Curiosity begins a slow, graceful drift inward. The halo of warped starlight grows more pronounced. The accretion disk is now a brilliant, blinding ribbon of fire filling half your viewport. The X-ray sensors are off the charts, and the ship's shields are beginning to strain under the bombardment. You're starting to feel uncomfortable, not from heat or vibration, but from something more subtle. So there you are, sitting in your command chair, the soft hum of the CSS Curiosity's failing systems, a constant reminder of your predicament. The black hole V74 fills the main viewport, a sphere of absolute blackness encircled by a furious, luminous whirlpool of superheated gas and a shimmering, twisted halo of background stars. You've decided to conduct a simple experiment, a touchstone of normalcy in a situation that is becoming increasingly not. You hold out your arm and you drop a pen. It clatters to the floor. Normal, right? For a split second, it feels like a victory, a reminder of the simple, predictable physics you left behind on Earth. But then, your trained eye, perhaps aided by the ship's high-resolution cameras replaying the event in slow motion, catches something peculiar. It was so subtle you almost missed it. The tip of the pen, the part closer to the black hole, seemed to fall just a tiny, tiny bit faster than the top of the pen. It wasn't a clean, uniform drop. It was as if an invisible, incredibly gentle hand had grabbed the pen's tip and given it an almost imperceptible extra tug, a microsecond before the top of the pen received the same command from gravity. It's a stretching, a gentle pulling. This, right here, is your first personal, tangible encounter with tidal forces. You are no longer just reading about them in a physics text. You are living them. Now, to truly understand what you just witnessed, we need to take a moment and unpack the idea of gravity itself. We often think of gravity as a force that just pulls us down, but it's much more nuanced than that. A great way to visualize it, as you recalled, is the rubber sheet analogy. Imagine space as a vast, stretchy trampoline mat. If you place a bowling ball in the center, it creates a deep dip. A marble rolled near the edge of this dip will spiral inward, not because some mysterious force is reaching out and grabbing it, but because it's simply following the curved path created by the bowling ball's weight. Now, a black hole isn't a bowling ball. It's an object so incredibly massive, with all that mass crushed into a point of such incomprehensible smallness that it doesn't just make a dip in the trampoline. It pulls the fabric down into an infinitely deep, narrow well, a puncture in the very fabric of space-time. The key thing to understand about this gravitational well is that its strength isn't uniform. The slope is steeper the closer you get to the center. This is true for Earth, too. The gravitational pull at your feet is technically minutely stronger than the pull at your head, because your feet are ever so slightly closer to the planet's center of mass. But the difference is so infinitesimally small, so utterly negligible, that you could never, ever perceive it. It's drowned out by every other force, from the blood pumping in your veins to the air conditioning in your room. Here, approaching V74, the game has changed entirely. The black hole's gravity is not just strong, it's intense, because all that immense mass is concentrated in such a small area. This allows you to get phenomenally close to the entire source of the gravity. The difference in the strength of the gravitational pull over a small distance, like the mere meter or so between the tip and the top of your pen, is no longer a tiny, theoretical calculation. It's a physical reality you can observe with your own eyes. The pen tip, being a centimeter or two closer to the black hole, feels a measurably stronger pull than the top of the pen. This difference in force across an object is the essence of a tidal force. Think of the ocean tides on Earth. The moon's gravity pulls on our planet. The side of Earth closest to the moon feels a stronger tug than the center of the planet, and the center feels a stronger tug than the far side. This difference stretches the Earth slightly, but most noticeably, it pulls the oceans into two bulges, one on the side facing the moon and one on the opposite side. That's a tidal force in action, a stretching caused by a difference in gravity. Now, imagine taking that gentle planetary scale stretching effect and cranking it up to an unimaginable degree. Imagine the difference in pull over the length of your body, or your ship, becoming so extreme that it behaves not like a solid object, but like a piece of soft toffee. This leads us directly to the fate you've just glimpsed with your pen. Now imagine your body is that pen. Your feet are closer to the black hole than your head. Because gravity is stronger the closer you are to the source, your feet are being pulled with significantly more force than your head. It's not a gentle suggestion, it's an irresistible command. At the same time, your left and right sides, being at roughly the same distance from the black hole, are both being pulled straight inward towards the central point, the singularity. This creates a competing effect, a squeezing, a compression from the sides. So, you are experiencing an intense, simultaneous, and terrifying combination of effects, a violent stretching from head to toe, and a powerful compression from your sides. This combination has a famous and rather pasta-themed name, one that was popularized by the legendary theoretical physicist Stephen Hawking. He described a fictional astronaut being stretched out like a long, thin strand of spaghetti, and the name stuck: spaghettification. It's an almost amusing name for a profoundly violent process. For a stellar mass black hole like your V74, which might be only about 30 miles across, the tidal forces are extreme right from the get-go. The gravitational gradient is unbelievably steep. The difference in gravity over just the height of your body is immense. So, as you fall in, this spaghettification process wouldn't be a slow, gradual stretching. It would become violent and swift. You wouldn't just feel stretched. Your body and your ship would be physically, irrevocably pulled apart. The bones, the muscles, the very atoms that make you you would be separated by an irresistible force, stretched into a stream of elementary particles spiraling inward. It would be instantly fatal. And this gruesome demise would happen well before you reached the most famous boundary, the event horizon, the point of no return. This is a crucial and often surprising point. The event horizon is the boundary beyond which not even light can escape. But it's not necessarily the point where you get turned into spaghetti. For a relatively small, stellar mass black hole, the tidal forces outside the event horizon are so ferocious that they would destroy any known material object long before it could cross that threshold. You would be shredded and incorporated into the hot, swirling plasma of the accretion disk, adding your mass and energy to the black hole from the outside. Your journey would end there, in a blinding flash of X-rays, a testament to the destructive power of the universe. But what if the black hole was different? This is where the story gets a fascinating twist. If you were falling towards a supermassive black hole, like the one at the center of our own Milky Way galaxy, which is millions of times more massive than the Sun, the situation would be strangely different. Because a supermassive black hole is so enormous, its event horizon is far, far out from the central point. The gravitational pull at the event horizon itself is much more spread out. The difference in gravity between your head and your feet at the moment you cross the event horizon could be so small that you might not even feel it. You could, in theory, cross the point of no return of a supermassive black hole intact and unharmed, at least for a little while. The real drama, the inevitable spaghettification, would begin after you were already inside, trapped. As you continued your fall toward the central singularity, where the tidal forces would once again become infinite and tear you apart. As NASA astrophysicist Jeremy Schnittman explains, if you have the choice, you want to fall into a supermassive black hole. Stellar mass black holes, which contain up to about 30 solar masses, possess much smaller event horizons and stronger tidal forces, which can rip apart approaching objects before they get to the horizon. So, as you sit there, staring at the pen on the floor, its tiny, almost imperceptible stretch is a quiet herald of an awesome power. It is the universe's way of demonstrating the raw geometric nature of gravity, not as a simple force, but as a curvature of space-time so severe that it can turn matter into streamers. That gentle tug on your pin is the same force that can tear entire stars apart, squeezing them like a tube of toothpaste, or flattening them into pancakes in a pancake detonation before swallowing their remains. It's a force that doesn't just content itself with bending the paths of light, creating those beautiful, impossible halos of distorted starlight around the black hole, but one that bends and stretches the very fabric of reality itself. And as the CSS Curiosity continues its inexorable fall, fighting a losing battle against a force that reshapes space and time, you now know with a chilling certainty that the normal rules of the universe you grew up with no longer apply. You have felt the first gentle whisper of the spaghetti monster, and you know that whisper will soon become a roar. So, for the sake of our story and our exploration, let's say the CSS Curiosity and you, its captain, are equipped with a hypothetical gravitational stabilization field that can somehow counteract the spaghettification effect, at least for a while. It's a device of pure imagination, allowing us to see what lies beyond. Because we are about to cross the ultimate boundary. You've resigned yourself to the fall. The engines have failed. The shields are buckling under the X-ray barrage from the accretion disk. You've passed the point of no return, in a practical sense, a while ago. But now you are approaching the final, mathematical point of no return, the event horizon. From the outside, the event horizon is a perfect, seamless, spherical boundary. It's not a physical surface you could bump into, it's a mathematical definition. It's the point where the escape velocity equals the speed of light. Since nothing can go faster than light, nothing that crosses this boundary can ever come back. Not a particle, not a signal, not a whisper of information. It is the ultimate cosmic prison wall. As you approach it, the universe outside is becoming distorted in impossible ways. Because of the extreme bending of light, you can now see the entire universe wrapped around you. Look forward toward the black hole, and you see only blackness. But look backward, or to the sides, and you see a rapidly shrinking bright disk of the entire cosmos, all of history and future compressed into a brilliant, blinding circle of light above you. It's like you're at the bottom of a well, looking up at the sky, but the well is closing shut. Commander Layla, on her station, sees your ship redshifted into invisibility. For her, you have effectively vanished from the universe. The last bit of light from your ship has been stretched into long wavelength radio waves, then into nothingness. To all intents and purposes, you have ceased to exist. The black hole, from her perspective, has just gained a tiny, tiny bit more mass, and its event horizon has expanded just a fraction. This relates to a profound idea from Stephen Hawking, called the area theorem, which states that the total area of a black hole's event horizon can never decrease. It can only stay the same or get bigger. You and your ship have become a permanent part of V-74's surface area, but for you, the journey is far from over. With our imaginary gravity stabilizer working at its limits, you cross the event horizon. One moment you're falling, the next, what? What is it like inside? This is the greatest mystery in all of physics. We don't know. We have equations and theories, but no data. No information ever comes out. But based on general relativity, we can theorize. The moment you cross event horizon, something fundamental flips. Outside the event horizon, you always had the freedom to move through space, but you were inevitably moving forward in time. Inside the event horizon, according to the mathematics, the roles of space and time reverse. The event horizon is behind you, or is it below you, or is it in your past? The very concepts of behind and ahead are beginning to feel slippery, like words in a language that no longer fits the world you're in. It is the single strangest sensation you have ever experienced, not a jolt or a sound, but a quiet, profound rewriting of the rules of existence. To understand what's happening, we need to think about what we've always taken for granted. Outside, in the regular universe, you have tremendous freedom of movement in space. You can go left or right, up or down, forward or backward. You can decide to walk to the kitchen, or run outside, or jump on a rocket and fly to Mars. Your movement through space is yours to command. But there's one direction in which you have absolutely no choice, no freedom at all. That direction is time. You are constantly, inexorably, moving forward in time from one second to the next. You cannot stop it. You cannot turn around and go back to yesterday. It is the most universal and undeniable fact of your life. The future becomes the present, which becomes the past. Inside the event horizon, according to the beautiful, terrifying mathematics of Einstein's general relativity, these two concepts, space and time, perform a cosmic swap. The direction toward the center of the black hole, the singularity, ceases to be just a location in space. It transforms. It becomes your future. Think about that for a moment. It's not just that you are moving toward a place. It is that the place itself is the embodiment of tomorrow. You are no longer traveling through space toward the singularity. You are quite literally traveling through time toward it. Just as you could not, out there in the safety of your home, avoid moving from breakfast time to lunchtime, you cannot now avoid moving toward the singularity. It is as inevitable as the next tick of the clock. This is not a matter of physics. It is a matter of destiny written into the very fabric of this new realm you now inhabit. This has a breathtaking and frankly horrifying consequence. On the outside, if you didn't like where you were, you could point your ship in any direction and, with enough fuel, go somewhere else. Inside the horizon, that freedom is gone. It has been stolen from you. Every possible direction you can point your ship, every vector you can plot on your navigation computer, every burst from your thrusters, it all points toward the center. It's as if your ship's compass has gone mad, and every needle, no matter how you shake it, spins unerringly toward the same single point, the singularity. turning your ship around and trying to go back toward the event horizon would be as futile as trying to travel back in time. You can't. The event horizon is not a place in space you can return to. It is now a moment in your past, and we all know you can't go back to the past. This is where that wonderful analogy of the river becomes so powerful. You are now in a region of space where the geometry, the very structure of space-time, is not static. It is flowing. It is collapsing inward at a fantastic, ever-increasing rate. Imagine you are in a small canoe on a vast, calm river that slowly, almost imperceptibly, begins to pick up speed. At first, it's pleasant, but then the current quickens. The river narrows. The gentle flow becomes a rush, then a torrent. You are now speeding toward a waterfall you can't yet see, but you can hear its roar. You panic. You grab your paddle, and you try with all your might to swim back upstream to fight the current. For a moment, you might even think you're making progress relative to the water immediately around you. But when you look at the riverbank, you realize a horrifying truth. You are still moving toward the waterfall, and faster than ever. Your paddling against the current only served to slow you down slightly, but the current itself is moving faster than you can possibly paddle. Now imagine that river is space-time itself, and the current is flowing faster than the speed of light. That is what it's like inside the event horizon. Firing your engines to escape is exactly like trying to swim upstream in that ultra-relativistic river. It is a task that is not just difficult, but fundamentally, physically impossible. There is no back anymore. The concept of away from the singularity has been erased from your dictionary. Every direction, every single one, leads forward to the center. You are a leaf caught in a cosmic drain, and the drain is pulling not just on you, but on the very space through which you are falling. Let's assume, for the sake of our incredible journey, that our ship's miraculous gravity stabilizers are still holding, shielding us from the tidal forces that would otherwise be already pulling us apart, like cosmic taffy. We are now deep inside the black hole, falling through the dark. It is a blackness so complete it feels heavy. It is not the black of a moonless night, or the black of the deepest ocean trench. This is the black of a place from which light itself cannot escape. The last glimpse of the outside universe, that brilliant, shrinking circle of light that contained every star, every galaxy, every memory you ever had, has now pinched off into a single, final, shining point, and then vanished. It is gone. The accretion disk, that furious whirlpool of energy, is now behind you, above the horizon. Its light can no longer reach you. There is no light. There is no sound. The only thing that exists is the faint, glowing readout on your instrument panels, and even those are beginning to flicker and display nonsense, their logic circuits overwhelmed by the extreme physics of this place. Now, according to the classic model of a simple, non-rotating black hole, a Schwarzschild black hole, there might be more structure inside than just an empty darkness leading to a point. You've crossed the outer event horizon, the point of no return we've discussed so much. But deeper in, the mathematics suggests there could be another boundary, an inner horizon. This is sometimes called the Cauchy horizon. This is a truly bizarre concept. In normal physics, if you know the state of a system now, you can use the laws of physics to predict its state in the future. This is the foundation of cause and effect. The Cauchy horizon is the boundary where this comfortable, predictable nature of the universe breaks down. Beyond this point, the equations of general relativity themselves become unstable. The future is no longer determined by the past. Cause and effect cease to have their firm meaning. It is a boundary of unpredictability. Why would this happen? Think of all the light and radiation that has ever fallen into this black hole over millions of years. From your perspective, falling inward, you are catching up with all of that history. The light from stars that fell in 1,000,000 years ago is still there, falling alongside you. As you approach this inner horizon, all of that energy, all of that light from the entire history of the black hole gets compressed into a vanishingly small space and time from your point of view. The wavelengths of that light get squashed, shifting to incredibly high energies. This is the blue shift effect, taken to an infinite extreme. Some theories suggest that this inner horizon is not a place of quiet darkness, but a searing wall of incandescent energy, a firewall of concentrated radiation with literally infinite energy density. It would be a wall of light so intense, so furious, that it would instantly vaporize anything and everything that contacts it. It would be a second final death far inside the event horizon. This idea of a firewall is a topic of fierce debate among physicists. It represents a crisis, a clash between Einstein's theory of general relativity, which predicts the existence of this inner horizon, and quantum mechanics, which abhors such infinities. The firewall paradox asks a brutal question. Is the inside of a black hole empty, as general relativity suggests, or is it guarded by a wall of fire, as this quantum mechanical line of thinking implies? We don't know. For you, the traveler, it means that even if you survive the crossing of the event horizon, your journey might end in a sudden, brilliant flash at this inner boundary, a final message from the universe that some territories are truly meant to be forbidden. Your instruments wouldn't just go haywire, they would be obliterated in a storm of energy that represents the accumulated history of the black hole itself, delivering its entire past to you in one single, unforgiving moment. And so, as you fall deeper into the absolute blackness, you are left to wonder, are you heading toward a silent, predictable end at the singularity, or are you about to sail directly into the universe's most ferocious and final cosmic fire? But let's say we survive that too. We are now falling through the final stretch. The gravity is becoming unimaginable. The tidal forces, even with our stabilizers, are starting to be felt. The ship is creaking. Loose objects are starting to stretch and drift toward the front. You feel a gentle but increasing pull on your feet. The singularity is near. What is the singularity? It's the heart of the black hole. According to general relativity, it's a point of infinite density where all the mass of the black hole is crushed into a volume of zero size. It's a place where the curvature of space-time becomes infinite, and the laws of physics as we know them simply stop working. Concepts of space, time, matter, and energy lose all meaning. It is the ultimate "here be dragons" on the map of the universe. You will never actually see the singularity or hit it in the conventional sense. As you approach, the tidal forces will become infinite. The difference in gravity between your head and your feet will be so vast that your body and your ship will be stretched into a stream of subatomic particles, and then the particles themselves will be torn apart. All the information that was you, your memories, your atoms, your quantum states, will be lost. Or will it? This is the famous black hole information paradox. To understand it, we need to think about what you really are. You are not just a collection of atoms. You are a very specific, intricate arrangement of those atoms. The type of atoms, their quantum states, their spins, their energies, all of this information is what makes you, you. It's what differentiates you from a cup of coffee or a passing comet. It's the blueprint of your existence. Now we have two sets of rules for how the universe works. The first is general relativity, Einstein's magnificent theory that describes the large-scale structure of space-time and gravity. General relativity, with its prediction of the singularity, seems to say that all the information that was you, your memories, your atoms, their unique quantum states, is utterly and permanently destroyed. It is lost in the infinite curvature of the singularity. The blueprint is incinerated, and there is no copy. From the perspective of general relativity, the black hole swallows the information, and it is gone forever. But then we have the other set of rules, quantum mechanics. Quantum mechanics is the rule book for the very small, the world of atoms and particles. And one of the most sacred, fundamental principles of quantum mechanics is that information can never be truly destroyed. It can be scrambled, it can be hidden, it can be transformed into something unrecognizable, but it can never vanish from the universe. The total amount of information must always be conserved. It's a cosmic law of you can't get rid of anything. If you burn a book, the information isn't gone. It's just transformed into the specific arrangement of smoke, ash, and heat. In principle, if you could collect every single atom of smoke and ash and measure the exact energy released, you could reconstruct the book. So, we have a direct conflict. General relativity says the black hole destroys information at the singularity. Quantum mechanics says that is absolutely forbidden. They can't both be right. This is the information paradox. It's a screaming alarm bell telling us that our understanding of physics is incomplete. This paradox is the key battleground for the holy grail of modern physics, a theory of quantum gravity. We need a single theory that can seamlessly unite the large-scale world of gravity, described by Einstein, with the small-scale world of quantum particles. A theory that can tell us what really happens at the center of a black hole. This is where we leave the solid ground of established science and venture into the thrilling, speculative frontiers of theoretical physics. Scientists are trying to solve this paradox, and their ideas are more incredible than any science fiction. Maybe the singularity isn't a point of infinite density. Perhaps, when we get down to this incredibly tiny scale, the weird effects of quantum mechanics take over. Gravity might become a quantum force, and this could prevent the formation of a true infinity. Instead of a singularity, there might be a tiny, incredibly dense, but finite object. Some call it a Planck star or a fuzzball. This object could be so small that it's beyond our ability to imagine, but it would have a finite surface and would not destroy information. Instead, it would hold on to it, scrambling it and eventually releasing it back into the universe over billions of years as the black hole evaporates via Hawking radiation. Perhaps there's a wormhole there, a tunnel through space-time, a shortcut to another part of our universe, or a gateway to an entirely different universe. In this scenario, the black hole isn't an end. It's a cosmic subway station. The information that was you would be ejected somewhere else, reassembled in a new reality. It's a beautiful idea, though there's no evidence for it. And the immense tidal forces and need for exotic matter to keep the wormhole open make it seem unlikely. Maybe, as some theories suggest, you become the seed for a new baby universe. In this mind-bending idea, the extreme conditions at the center of the black hole cause a bubble of space-time to pinch off from our own. This new universe, with its own laws of physics, begins its own Big Bang, and the information that was you becomes part of the fundamental seed from which an entire cosmos grows. You wouldn't be conscious in this new universe. You would be part of its very foundation. It's a poetic thought that every black hole in our universe might be giving birth to a new one, a vast, branching multiverse of cosmic offspring. These are thrilling, spectacular ideas. They fire the imagination and show us just how strange the cosmos might be. But we must be honest. The hard, humble truth, based on our current knowledge, is that we don't know which, if any, of these possibilities is correct. For you, the traveler in our story, the journey, as far as classical physics is concerned, ends at the singularity. It is the end of your timeline, the end of your space-time. The infinite tidal forces ensure that the complex structure that is you is erased from the cosmic ledger. The black hole information paradox remains just that, a paradox, a question mark at the heart of darkness, challenging us to think deeper, to look further, and to never stop wondering about the ultimate fate that awaits in the abyss. But wait, what about the black hole itself? Does it last forever? Stephen Hawking shocked the world in 1974 with a revolutionary idea. He proposed that black holes are not entirely black. They aren't the perfect traps we thought they were. He applied quantum mechanics to the space just outside the event horizon. In empty space, pairs of virtual particles are constantly popping into existence and then annihilating each other almost instantly. This is a well-known quantum quirk. Hawking said, if this happens right at the event horizon, one particle of the pair could fall into the black hole, while the other escapes into space. The escaped particle becomes real, carrying away energy. This stream of escaping particles is called Hawking radiation. Where does the energy come from? It comes from the mass of the black hole itself. To an outside observer, the black hole is slowly losing mass, slowly evaporating. This process is incredibly slow for a stellar mass black hole. It would take many, many times the current age of the universe for one to evaporate. But for smaller, hypothetical black holes, it could be much faster. This is where our story connects to one of the most exciting frontiers in science today. What happens at the very end of a black hole's life, when it has evaporated through Hawking radiation down to almost nothing? Many physicists believe it ends in a titanic explosion, a final burst of particles and energy that would be the most powerful event since the Big Bang. And there is a specific thrilling search for this very phenomenon. Scientists are looking for primordial black holes, PBHs. These are not born from dying stars, but are thought to have been created in the incredibly dense, hot conditions of the early universe, a fraction of a second after the Big Bang. They could be much smaller than stellar black holes, some as small as asteroids or even pebbles. And if they exist, the smallest of them would be reaching the end of their lives and exploding right now. A team from the University of Massachusetts Amherst has even calculated that if these PBHs have certain properties, like a tiny electric charge from a hypothetical dark electron, then we might see one explode as often as once every decade, and our current telescopes might be able to spot it. They give it a 90% chance in the next 10 years. Can you imagine? To see a black hole die? It would be a revolution in physics. What would such an explosion look like? It wouldn't be a fireball in the conventional sense. It would be a flood of particles, a complete sampler of every fundamental particle that exists in the universe, not just the ones we know, electrons, quarks, neutrinos, but also the ones we don't, the particles that make up dark matter, the known unknowns, and perhaps even the unknown unknowns. It would be like the universe's final exam, a complete answer key to the building blocks of reality. As one researcher said, it would completely revolutionize physics and help us rewrite the history of the universe. In fact, just recently, scientists detected a mysteriously energetic neutrino, a ghost particle, from space. Researchers at MIT have proposed that this ultra-high energy particle could have come from the explosion of a nearby primordial black hole. If so, it might be our first ever indirect detection of Hawking radiation, a glimpse of a black hole's final moments. So, as you, the captain of the CSS Curiosity, fall toward your inevitable end in the singularity of V74, know that the story of black holes is far bigger than a single journey. Your black hole will live for eons, a stable fixture in the galaxy. But elsewhere, tiny ancient black holes from the dawn of time might be lighting up the cosmos with their death cries, offering us the keys to unlock the universe's deepest secrets. Your journey is nearly over. The pull is now irresistible. The ship's stabilizers are failing. The darkness ahead is absolute. The instruments have given up, their readings nonsensical. You are at the frontier of knowledge, at the edge of physics itself. What happens next is the greatest mystery. Is it nothingness, oblivion, or is it a transformation into something beyond our comprehension? We simply don't know. It is a blank space on the map, a question that keeps scientists awake at night. It is a reminder of the humble truth of science. The more we know, the more we realize how much we have yet to discover. Your ship and you become one with the singularity. The information that was you is lost to our universe. But perhaps, in some way we cannot yet imagine, it is preserved on the event horizon, a holographic fossil of your final journey. Or perhaps it fuels the birth of a new cosmos in a multiverse we can never see. The black hole, V74, continues to spin in the silence. From the outside, it is a quiet, dark sphere, a perfect cosmic secret keeper. The accretion disk still glows. Stars still slide around it in their distorted orbits. Commander Layla marks the log, a moment of silence for a lost explorer and a lost ship. But she and scientists across the galaxy continue to watch and to listen. Because the universe is speaking to us. It speaks in the gravitational waves that ripple out from colliding black holes, vibrations in space-time that confirm Einstein's and Hawking's predictions. It speaks in the high-energy neutrinos that might be the whispers of dying primordial black holes. It speaks in the warped starlight around these dark monsters. Our journey into the black hole was a one-way trip, but the journey of understanding, the human drive to explore and know, is endless. The black hole is not an end. It is an invitation to push further, to think deeper, to imagine the impossible. It is a symbol of the ultimate unknown and our eternal desire to bring it into the light. And so, we find ourselves returning from the very edge of reality, from the infinite density of the singularity and the cosmic fireworks of dying black holes, back to the quiet comfort of our own room, our own world. It's a lot to take in, isn't it? The sheer scale, the mystery, the terrifying beauty of it all. Black holes remind us that the universe is far stranger and more wonderful than we could ever imagine, and that some of the greatest adventures are the ones we take in our minds. I hope this journey into the cosmic abyss has filled you with a sense of wonder and given your mind a vast, peaceful expanse to wander through as you begin to drift off. If it helped you unwind and escape for a while, I'd be so grateful if you'd tap that like button. It lets me know which journeys you enjoy most. If you haven't already, please consider subscribing to Hey-Fi Sleep and ringing the bell. There are so many more mysteries to explore together, from the birth of stars to the nature of time itself. And I'd love for you to join me on the next adventure. And as always, I'd be delighted to hear from you. Drop a comment below and tell me, where are you watching from tonight? And what part of this black hole journey will you be taking with you into your dreams? Hearing from our global community of curious minds is one of my favorite things. From all of us here at Hey-Fi Sleep, thank you for listening. Wherever you are, whatever the time, we wish you a night of profound peace, captivating dreams, and restful sleep. Good night, my friends.